good afternoon to all the people here. For me, it's a pleasure being the third time in a row in HPC KP. Actually, it's my fifth HPC KP in all my life, but it's the third in a row. The first one, I was speaking about quantum computing. The second one, I was helping the panelists. And the third one, I'm here again talking about quantum computing. That is one of my passions. So today I'm here representing Qilimanjaro, where I work in there since 1 month ago, a solution architect. And I will show you our presentation titled Qilimanjaro and the Democratization of Quantum Computing through HPC Integration. So just let me start by saying what we do in Qilimanjaro. Qilimanjaro is a startup coming from BSc and other centers that is not so far away from here. You can take a bus and go strictly to the office. It's in Selva de Mar, close to the beach in Barcelona. And we build full-stack analog quantum computers. I will enter into detail of what it is. We build it, as you can see in the picture. We have here David Slava, one of my coworkers, that is fixing a GPU in the fridge. And we do it we build full-stack analog quantum computers from the chip to the user without leaving any state in the middle. So just to show you the stack of all the things that we do in Qilimanjaro, starting from the user point of view and finishing in the chip, one thing that we do is we will have, not yet, a user interface that can help the user understand the chip and the technology and see how the jobs that they submit to the platform works. Then we have an algorithm portfolio that is built by our algorithms and applications team with some use cases, at the moment not really useful use cases, as you may know from the current state of the technology, but at least something that can be then adapted once we get to the quantum supremacy in some years ago. Then we have also the programming framework to make the quantum computer work and also to understand the algorithms that the user sends. And just below that, we have what we call the cloud access. That is the piece of software that will make the user interact with a quantum computer. After that, we have the hardware control. It's also a piece of hardware and software that translates the Python circuits or the Python objects to real signals, pulses that send to via the control electronics. That is these blue things here. And then this control electronics is the one that communicates with the QPUs, the quantum processing units, the digital QPUs, the analog QPUs, and also the emulator that can skip all the control electronics. We also have a team called setup integration that are the ones that are devoted to do all installation of quantum computers in HPC centers, like the ones that they are in BSc. So you can imagine that for doing all these big amount of things, we need a big team, and this is the case. So for now, that was information from Friday. This information is updated almost every week. We are 75 employees, 5 of them are interns. From them, we are 17 PhDs, 45 quantum engineers of more than 10 nationalities. And here it's not here in the slide because we don't want to say that as a flag, but the 30% of the company are women. And not only in the non-technical part, we have also a big amount of female power in the technical side. So moving above is what makes us different. So when you think about quantum computer, you can think about IBM, that has these very big quantum computers, and the one that is coming here in Spain soon. You can think about Google. We can think of these Majoranas from Microsoft. And what is the difference that they have and what we have and they not? Is what we call the computation model. For those of you that already play a little bit with quantum computers, you will be familiar with this thing, this like a pentagram with the different qubits, where are different quantum gates, for example, the Hadamard, that is the stage, or the control node, that is the one here, playing in these 2 qubits. And this is the way how it's programmed. So you have your algorithm, you code in gates in a similar way that we in classical computing play with assembler, saying, okay, qubit 1, you will be affected by a Hadamard, and then you will have, conjointly with the qubit 2, be affected by the CNOT gate. So this way to applying discrete operations in the qubit, because every box that we have here is a hit that the control electronics has to do to the chip. It has associated a small error. And if this is a very small circuit and has not too many errors associated, but try to imagine a very long circuit, the one that is, for example, the short algorithm, that will be this future use case will be the decryption of keys, and can be quite locked, and has to be, and will have a very big error associated to that. So what we do is we do analog quantum computing. The way that we apply the signals is not by hitting the qubits each time that we are operating that, is by applying a continuous flow of information. I haven't put it here to don't scare you, but the way to work on that is using a Hamiltonian. That is a function that depends on some parameters of the qubit. So what we do is, at the very beginning, I pointed with the finger because I have told that the pointer is not seen at the end. At the very beginning, we set an initial state, initial Hamiltonian, a function, let's say, that is easy to prepare. And then we play, or the person behind the algorithm plays a little bit with the parameters of the qubit to make the state evolve fluently to the final state of the minimal energy. So the way, and also you can imagine the way to code that it's a little bit different. So to summarize a little bit the big difference and why we go to analog quantum computing, in digital, we have to perform error correction techniques because we are getting some errors. There are different ones. One of them involves the aggregation of different physical qubits in boxes that are the logical qubits, and that makes the chip lose a lot of qubit count. So you have, for example, a 1,000 supercomputing digital QPU, and then you want to apply error correction using logical qubits, you might end up with 50 logical qubits at the end, or 100 in the best case scenario. Then other thing that we have in analog quantum computer is that as we are not hitting, as I commented before, the qubit each time, we are evolving it slowly, we are less prone to errors. And especially in our case, we have some parameter that's quite important in quantum computing, that is the coherence, is the time that the chip keeps alive, let's say. The type of qubit, the physical implementation, the circuit that we use to map the qubit, it has longer coherences due to the nature of the system that we are doing, of the fluxonium, than the transmode that are the other ones. So moving ahead, and just to summarize what we choose this alternative in Qilimanjaro, we want to bypass the error correction protocols to have a big qubit count with quality qubits inside. Then we want to have long coherence times in our chips to be able to perform some simulations longer than the one. And we tailor to specific solutions. We have our own algorithms team. It's like, you can imagine, for example, the Apple ecosystem, when you have your devices, and you have applications that are only working for this kind of devices. So it's something similar that we are doing. And what kind of solutions we are solving to that? So we focus on the quantum description of the nature, because as Richard Feynman said, the nature isn't classical. And if we add here, it's not digital. Damn it. So this is the approach that we follow. And this is not something that we say, OK, we have some few numbers to say we can do that. We have another reason to move in that way, is just repeating the history. So we have, half a century ago, we know because we are not even born, but there was these big quantum computers that were analog and are app-specific, and it ends up to the small chips that we can wear in our arm. So just to finish a little bit with the corporative stuff, otherwise Jordi will say you have to be more technical. We have 3 verticals in our company, so 3 main business models. The first one is the quantum as a service. I will enter into detail what it is. Then we have also the quantum exploratory services, and then the quantum computing on-premise. I will go fast to each of them. For the quantum computing, for quantum as a service, we will release at the end of the year what we call our portal. This is just a mock-up of the web portal that the user will be able to see, but it's all the system behind that will let the users use our quantum computers. So the way to do that is that the user will have some code examples, or they will know how to do that. They will have an API or a token to log into our system, run the jobs, and there in this panel they will see the results, and also the calibration information and all the different relevant information that they may need. Then we offer also quantum exploratory services. So we know, and we are trying very hard to be 100% hype-free guaranteed, is that show to the people that for the moment there is no practical use of quantum computing. We can, or our users can play with it a little bit, can play with interaction of quantum computing with classical ones, can play with some circuits or to approximate to certain problem, but to the moment it's not. And what we are doing is helping our customers to become ready when the time will go. And last, this is our star, let's say, our best solution that we have for the moment. Is the first hybrid development that we have. And as far as I know, the first hybrid for superconducting qubits. This is what is now in BSC, something that you will see tomorrow. There are 2 quantum computers at the same time, together in this site, and I will take this picture just to show you how the quantum computer works. So here, this kind of barrel is what we call the fridge. It contains, I don't have here a picture, but it's this sort of golden chandelier. It keeps the chip cold. Here we have all the vacuum and all the electronics and all the pump necessary to put this part of the fridge at 15 millikelvin. And everything is connected through a server that it will be there. So the control electronics that I commented before is in the upper position. It is covered and is not shown for this picture, but is connected to the fridge. And then from that, there is a switch that connects to a lot of Ethernet cables that control the system. And then from that switch, it connects to a server that is the one that's called the control and the connection to the cluster. So let me explain a little bit about this hybrid development and the 2 projects that are making that possible. The first one is QuantumSpain. This project is from this 100% from Spain. And among other things that they are doing, because they are providing training, a lot of information, a lot of seminars, is the installation of a quantum computer there. So in that case, we install a digital quantum computer. The chip is not seen here. Well, if you look carefully, you can see the logo of the vendor of the chip that is Quanware. So Qilimanjaro, in that case, did the setup integration, mounting all the different parts of the quantum computer. And then a classical vendor called GMV did the interconnection with the cluster and all the communication between the cluster and the QPU. Just for you, for curiosity, this project cost, not the project, the installation of the GPU cost 8 million euros, 8.1, and is managed by the Red Española Supercomputación. So they opened access to this quantum computer, and they closed it a month ago, I think, and they closed it, I don't know if it was 2 weeks ago. And soon we will have our own, well, BSC will have the first users working in using this system. About the out the two systems that we have there are two from Quantum-Spain. And we have two because in the meantime that there is one working, the other one will be upgraded. So now we have in BSC, we have already updated from 5 qubits that is in the blue system to 10 qubits that is in the red one. And during this month, we will remove the 5-qubit chip to the blue one and we'll put the 20. And then at the end of this September, we will deliver the last delivery, of course, of the system with 35 qubits. That is what we agreed in the project. So how it is connected to Mare Nostrum? It was quite straightforward in the point of view of HPC, because as the two quantum computers are connected to a server, this server is taken into consideration as a node. And for that reason, we can apply, not we, it was BSC, they did two partitions that they call Q red and Q blue, and then connecting them to Mare Nostrum 5. At the moment, there are two different systems, but they have plans to put everything together. Yes, I don't want to forget that thing. So this is the first paper that has been published using Qilimanjaro quantum computers. It's by the group of Rosa Maria Badia from the PyComs team. Maybe it can ring you a bell. So it was the people from her team did an implementation of PyComs using doing circuit cutting for test the interconnection of the quantum computer and the classical one. So with circuit cutting, I mean, you remember that thing? When they started to work on that paper, the system has 5 qubits. And what they did is design an algorithm that is using more than 5 qubits and find a proper way to cut the circuit in pieces of up to 5 qubits to be ready to run in the system. You want to see how it goes? This paper is in archive. Yeah, and it's pretty nice to read. Then we are jumping to the new project that is the EuroQCS-Spain. This project started this year. And as the difference between the project is the technology of the QPU that we are using. In that case, we are manufacturing our own chip to put in here, something that is in progress right now. The budget is more or less the same. And we will start installation in late 25, late this year. The fabrication of the chip and all interconnection of all the different parts of the quantum computer will be done by Qilimanjaro. And the connection of the quantum computer to the previous Mare Nostrum MONA cluster and Mare Nostrum and all the things that is requiring, plus installation of the software and this task will be done by DuoIT now. This project is made by EuroQCS undertaking in the way that if you want to access that, maybe it would be, I can imagine that mid-26, you have to apply for EuroQCS in the same way that you can apply for having some computational power from Mare Nostrum, from the Ocalion, or for the other ones, and use it. So we'll skip super fast the number of qubits because I did a mistake in the slide. But we will deliver a 10 qubits system in 3 different phases, changing the connectivity, so changing how many qubits are connected to all of them. Because as bigger connectivity you will have, better algorithms you can run there. Then, how this system will be plugged with Mare Nostrum MONA. So the idea is using the same approach that we have there. So we will have, I simplify a little bit, but the new device, the color is not decided. So there is someone from the BSC here in the system is not decided. I put it that just to emphasize, but it's something that has been decided by the customer. So the QPU, the new QPU with the analog superconducting chip will be connected to another server, and this server will be connected to the Mare Nostrum MONA one. And just to give you some examples, okay, I have time. Just to give you some example of what can we do with this hybrid digital superconducting and analog superconducting system, I have some papers from here from different people that make that ready the effort to study that. So here is a study doing two-body Hamiltonians, another one doing quantum optimization with trap ions, and another one simulating fermionic models. But as we are not quantum physicists, or at least not the 100% of the audience, I will translate in real cases. That will be the perfect scenario for running optimization problems. So for example, something that can be solved is for logistics. That imagine a company like Glovo, like Stuart, that they have different riders. So the way that they have to deploy the riders to get the different packages that they have. Or try to imagine the chaos inside Amazon when we are ordering a toothbrush, SD card, and a box of napkins. So the person or the robot that has to go to the warehouse looking for that thing, that different things will take their time navigating through the warehouse. There's something that can be speed up. And another one that I didn't know that was a problem, but was very, very, now that when they told me was, you're okay, you're right, is in operating room optimization. When someone is getting operated, there are a lot of things happening at the same time that has to be properly orchestrated. And also have to be, well, it's a good use case for the future of hybrid quantum computing. Then, I told you that you can access to the digital one applying to the rest, but now it's closed. I told you that you can apply for the analog quantum computing applying to HPC, but it will be open in the next year. But you can start soon, in November, apply to our hybrid quantum as a service. We are opening our beta access to our hybrid and analog superconducting cluster that we will have in our office. At the end of the year, we are not close to say not only academic or not only industrial. We are open to anyone that wants to participate as soon as they are doing an R&D activity on that. So it's just to avoid to have 100 of applications saying I want to run a calculator. And we are targeting some use cases that we can add in the previous slide instead of doing a wishful thinking of what it will be the next things to have running in the computer, put in real cases, and has free access limited to the beta duration. And for that, I'm finished. Here we have the details of the quantum as a service and exploratory services that we have. And here you have my contact in the case you want to ask me something. And maybe the business guy will kill me, but I invite you want to see our lab, just drop me an email and we can find a visit there. Thank you.
Thank you so much. We have time for some questions. Awesome.
Yeah, sorry, because you were talking about the coherence time, and you told that the analog quantum computing has longer coherence time than the digital one. But what are those times, and if you know, and how do they affect the length of a quantum computation that you can do? Because I imagine that if it is not coherent, you cannot longer use these qubits, no? Is like that? Or
yeah, it's like that. It's like that. The difference is not in pure analog and pure digital, the coherence times are different. Is that in the weight, in the chip that we are doing, that is a fluxonium, it has, I can be technical with that. So the difference between both, the transmon chip, that is the one that is used for mostly all the digitals, there are different. And the one that we use is that our own has inductance that shields a little bit the system. So it makes the system has less prone to errors and less affected. And that increases the coherence time. So as longer coherence time do we have, as long the circuits or the simulations can be. In our case of superconducting, I don't know what is the current state of the art, but a couple of years ago when I was doing the master was milliseconds, around milliseconds. For now, I don't have it clear. There are other technologies, like, for example, analog quantum computing using neutral atoms, that the coherence time are seconds, even minutes. because of the technology that they use. But they have other drawbacks.
Anything else? No? Well, I have a question for you. I know you're quite a visionary, and you said the words quantum supremacy, and to me supremacy is a big word.
I say supremacy.
So what's your forecast on that? It's really a supremacy, or the people who are doing classical computing, we should start to learn quantum because we're going together?
No. Here I'm speaking like Eli, not like Qilimanjaro. The way that I forecast that quantum computer will work in HPC is in the same way that we are using GPUs. So now we have regular CPUs working with GPUs. In the future, we will have CPUs working with GPUs and working with GPUs. So it will not be a replacement, but it will be like an accelerator in a way. And I suppose that this is also my personal bet, not Qilimanjaro one, that we will start seeing something interesting in 5 years.
So in 5 years, we'll have an open on-demand for quantum resources?
Now we can use open on-demand to access to the quantum computers because it's just another partition that we have in the system. You can connect to our interactive node with open on-demand and send the circuit to the partition when the system is running.
Okay, thank you, Eli.
Welcome.
Oh, another question.
How would you convince somebody that is doing computer architecture studying, getting into a master course or a PhD, how would you convince them to do their research in the field of computing for quantum computers instead of the regular digital computers?
That's a good question, because I was almost there, and I moved to quantum because of the challenge that it brings for classical, or what we call conventional or regular computation. There is still a lot of things to be discovered. It's not a closed thing. It's nothing dead. It is still very, very alive. But the challenge that brings quantum computing is that, OK, we have something that we don't know if it will work. Of all the startups, quantum startups will have to close in 10 years. So it's like a betting of, not that if you are brave enough to change the world, let's say, is that you want to try something that is so experimental. It's like the same case with neuromorphic computing, using brain cells to build AI. It's something that the people have to start working in the classical field? No. It's something that can be a little bit explored. So I will not say yes, no in that thing, as I'm quantum. So I will say that a combination of the two things will work.
Another one? Oh, let's see.
How is the status about the quantum compilers? I know that there are different architectures. Every architecture need to submit in a different code.
Yeah.
And I know that there are some efforts in this way. But what do you expect about that?
I hopefully expect that we arrive to a final agreement to have mostly the same compilers. So there is a group in Munich, I don't remember, Munich Quantum Computing Center, I think it is, that they have a solution to standardize the connection with the coding of quantum computers to one to the other. Because in one side is the way that the user codes that can be the most similar. For example, NVIDIA with CUDA Quantum has their own backend that they can run circuits and also Hamiltonians. I think, if I don't count, up to 8 different technologies, different quantum computers. So this is one thing that, okay, there are some efforts doing that because otherwise we will have each our own. Even us, we have our own library that is called Qili SDK. And then the other thing is how these circuits are written by the user are translated to pulses that are sent to the quantum computer. So I think that second point is the most challenging one. Because for the example that I put you for CUDA, they only do the submission of the circuit. Then internally, each company takes the object of this circuit and they convert to their own format and then run the electronics. But yes, so the idea is from the point of view for the user is doing as simple as possible, trying to democratize all the usage of the different quantum computers because we don't know which will be the winning technology. But for the point of view of the interaction from the electronics point of view, I think that it will not be standardized. I hope so, but I think no, that will be a very big challenge.
Okay, so if anybody else wants to ask something, I think we can all thank again to Elisabeth.